Thank you, Vela. And yeah, so I'm talking a little bit about how robots work, starting with walking robots. And yeah, as Vela mentioned, one thing we'd like to do, and one reason to motivate walking robots, is that they're really good at going places that sort of people and other robots can't. So you can take these guys and strap some sensor packages onto them, and you can then send them into some sort of, like, for example, in Myanmar, after an earthquake, and you can then build up a 3D map of what the environment looks like, which means you can then show to the people, to the experts, exactly what's going on before they go in themselves, which can hopefully save their lives. Cool. So how do actually walking robots, how do they work? So the most prominent method, or sort of one of the most popular ones, is something called reinforcement learning, which is a bit like having robots teach themselves to walk. So you create essentially 1,000 virtual robots in sort of a gym, and you basically probe them so that they walk, and if they fall over, you restart them. And the one robot that's the best sort of then becomes repeated again, and you completely repeat this process until you end up with a really nice policy. And that's currently one of the best methods. However, there are a few shortcomings. And one of them is you don't always know what you're going to get. So, for example, we have a robot that comes with a RL, reinforcement learning policy, on it, but we can't go more than 2 meters close to it, which is kind of an issue if we want to work with our robots. So what other methods could we use, maybe? So that's what my research is all about. And here we've got a picture of a blender. So what I did was, in order to come up with a method which was sort of interpretable and understandable, was we take lots of examples of robots walking from lots of different experts, and then we put them into sort of our blender. It's actually a variational autoencoder, or VAE, and we get out our smoothie or latent space. So it's a bit like putting lots of fruit with lots of different flavors into your blender, and then your smoothie comes out with one distinct flavor. So what is a latent space, and how does it help us walk? So this is what it looks like for locomotion. So we have all these experts, and we create this latent space. And each point is a robot in a different configuration. So configuration might be something like this, could be something like that, for instance. And then the colors denote which feet are on the ground. So the dark blue bit, the big bit in the middle, is both feet are in contact, for a human at least. And then the orange one is 1 foot is in the air. And then the blue is back to 2 feet. And then the teal, sort of greeny bit, is on the other foot in the air. So as you can see, as I walk, I'll be moving from the blue to the orange, back to the blue, and then to the teal. And that's really nice, because now we have a 2D manifold where we can then control a very complicated robot, and that's really easy to understand, at least for me. I'm quite simple. We then showed it to a neuroscientist, and he said, you know what, this looks a lot like what happens in your motor cortex. So this is a monkey, and if you get the monkey to walk and you look inside their motor cortex, you'll see these sort of circular patterns. So the neurons will fire in 3D. If you project that onto a 2D surface, like a piece of paper, it'll look like a circle. And then that looks really similar to what we have in our robot's brain. So we were like, whoa, what have we done? We found something really cool. And we're really excited, right? Because science, right? So we then thought, okay, let's try it on the robot and see if it works. And then, if it will start, yeah. It didn't work. It was rubbish. It was a disaster. This is like one of the lowest points of my life, which is kind of sad, but also you can see it was just rubbish. Oh, anyway, I'm gonna get rid of that because it brings back too many bad memories. So I didn't know what to do. I thought we had something really cool, but it just doesn't work. So I went home and I went for a walk because I quite like walking, and I was with my parents, and I couldn't get this problem out of my mind. It was just stuck in there. Just like a terrible song. And as I was walking, I tripped over like a root, and my feet went really fast so I didn't fall over. And in that moment, I realized, hang on, we've been looking at the signals when the robot walks, but what happened when I tripped is that my brain, the signals went really quickly to help me stabilize. So if I inject the signals into the latent space and then decode them, maybe my robot would walk. So I went back straight to Oxford to try it, and it worked. Oh, relief. Thank God. So yeah, so I can explain a bit more about exactly how it works. So this is the same image again, and what's really cool about this is if you've got this sort of circle in the latent space, so the robot's walking, if you kind of stretch the circle out in the horizontal axis, the robot takes really long, really sort of tall footsteps. And if you make it really narrow, it takes really tiny footsteps. And then the same for like the length as well, but in the other direction. So that's pretty cool, because now you can kind of like mix up different types of motion. You get the robots to sort of almost dance, basically. And then I thought, you know what? What happens if I sort of stretch my analogy of me tripping, sort of speed up the footsteps? And because the robot's walking, I can actually try it. So that's what you'll see here. So this is my friend Wolfgang. He's going to bully the robot. And when the robot gets bullied, it will take really fast steps, like when I tripped. And actually, it works quite well. So we could actually show, if the robot doesn't do this behavior, you can push it over quite easily. But if you do this kind of behavior, you can push it really hard. And again, we're both roboticists, so we spent many hours and late nights when this wasn't working. So to push it was quite stress relieving. But we work with robots. Cool. All right. So we also want to do terrain, because then we can send these robots off into Myanmar and they can go and they can do useful things, which is what we really want. And what's happening here is, as I mentioned before, you can kind of mix up different types of locomotion, because what you can do is if the robot needs to take a very long footstep, say, I don't know, you're stepping onto something, you need a long footstep, you can have a very sort of eccentric motion in the vertical axis and the horizontal axis. And that's what you'll see just now. So you get a really stretched out trajectory and the robot's able to sort of walk onto this step. So that's pretty nice, because we've got a robot that's stable enough to be pushed, walk over uneven terrain, but also, with vision, can overcome obstacles. That's pretty cool. So now I'm just going to sort of tease a bit more about what we're doing sort of in the future. So now we have this bimanual robot. So this looks a bit more like half a human. And rather than having 4 legs, we have 2 arms. So a bit like a motor cortex. And what we're trying to do here is we want this robot to be assistive, so it can go into care homes, can help deliver water to people who are dehydrated. One of the biggest killers in care homes is dehydration. And also we want it to build things. And of course play with it, interact with it, as you would like a human. And one of the cool things about that is we're taking the research from locomotion, from the motor cortex. We're trying to take inspiration from other parts of the brain, like the hippocampus, where memories are stored. And we're trying to sort of like merge these two together so that we can end up with policies that are able to build things, so do very high level planning, long horizon planning, and be much more useful than just being able to take payloads. So you can take this robot, ideally somewhere like even in Myanmar, it can go do, and then it can use its hands to do useful things. So that's just sort of a teaser of what we're doing next, and I'm very happy to take questions.